Welcome to The Explainer. So, you're prepping for your CEH certification, and let's be honest, cryptography can feel, well, like a total beast. Don't worry, today we're going to cut right through all that noise. We're focusing on the absolute must-know concepts and algorithms you need to nail this thing. Let's jump in.
So, here's our game plan. First, we're going to look at the why, cryptography's 4 pillars. Then we'll get into the big debate, symmetric versus asymmetric keys. After that, we'll meet the actual algorithms you'll see on the exam. And finally, we'll cover hashing and digital signatures, wrapping it all up with how to think about this stuff to pass your CEH. All right, first things first. Before we dive into the how, we really need to get a grip on the why. What problems is cryptography actually trying to solve? You know, it's not just about keeping secrets, it's about creating trust in this completely digital world we live in.
And these are the big 4, the foundational goals. Think of them like this. Confidentiality is the lock. It keeps your stuff secret. Integrity is the tamper-proof seal. It proves your data hasn't been messed with. Authentication is like a fingerprint. It proves you are who you say you are. And then there's non-repudiation, the legally binding signature. Let's zoom in on that one.
Now, non-repudiation is super important, especially for the CEH exam, because this is where the tech hits the real world, even the legal world. It's all about undeniable proof. It answers that critical question: can you prove without a shadow of a doubt that someone sent this message and they can't just deny it later?
Right, so the key here is proof. Proof of origin and proof of receipt. Imagine a big business deal gets finalized over email. If one person tries to back out later and claims, I never sent that, non-repudiation is the mechanism, usually through a digital signature, that proves they absolutely did.
Okay, so we know why we're doing all this. Now let's get into the 2 main ways we actually make it happen. You know, every modern encryption system you'll ever run into fits into one of these 2 buckets. And the big difference? It's all about the keys.
And this slide really lays out the fundamental trade-off. On one hand, you have symmetric encryption. It uses one single shared key. It's blazing fast, perfect for encrypting, say, your whole hard drive. But how do you securely share that one key to begin with? That's its big weakness. On the other hand, asymmetric, or public key crypto, solves that problem with a public and private key pair. But the catch? It's way slower and hungry for processing power.
All right, now for the actual tools of the trade. For your CEH, you don't need to be some crypto mathematician, but you absolutely have to recognize these algorithms, know if they're symmetric or asymmetric, and have a good idea of what they're used for.
Let's kick things off with symmetric algorithms. Think of these as the heavy lifters, the workhorses of the crypto world. Because they use that one shared key, they're super efficient. This makes them perfect for encrypting massive amounts of data, like a huge video file or your entire laptop with BitLocker. Here's your cheat sheet. DES? That's the old, broken one. Forget it. 3DES was the temporary fix, but the one you really need to know is AES. And pay attention to those numbers. AES uses a 128-bit block and keys up to 256 bits. These little details are prime material for exam questions. And this is a huge takeaway. Seriously burn this into your brain. If you see a question on the CEH asking for the modern, secure, industry-standard cipher for encrypting lots of data, the answer is almost always going to be AES. It's the gold standard today, period.
Okay, now for the other side of the coin, asymmetric algorithms. Remember, these are the slower ones. You're not going to encrypt a whole terabyte drive with these. Instead, they do these really specialized, super-critical jobs, like securely exchanging the keys for the fast, symmetric encryption, or creating those digital signatures we talked about.
Diffie-Hellman is it's pure genius. It lets 2 people, say you and your bank's website, create a shared secret key, like an AES key, right over the open, untrusted internet, without ever actually sending the key itself. It's the elegant solution to that nagging key-sharing problem that symmetric encryption has.
So we've talked a lot about confidentiality, right? Keeping secrets. But what about those other pillars? How do we prove a file hasn't been changed? Integrity. Or that it really came from the person who says they sent it, authentication. Well, for that, we have a different tool, hashing.
The key phrase here, the one to remember, is one-way function. You can take any file, run it through a hash function, and get a unique fingerprint. But, and this is crucial, you can't take that fingerprint and go backward to get the file. It's also designed so that changing even a single comma in the original file completely and unpredictably changes the hash. Now,
For the exam, this is non-negotiable. You must know that MD5 and SHA-1 are broken. They're dead. Don't use them. They suffer from what are called collisions, where attackers can create two different files that have the exact same hash. The current standards you need to know are SHA-2 and its more modern cousin, SHA-3.
And this is where it all comes together in a beautiful way. We're not encrypting the whole message, right? We just create that little hash fingerprint. Then, the sender encrypts that tiny hash with their private key. That encrypted hash is the digital signature. So on the other end, the recipient uses the sender's public key to decrypt it. If it works, boom, that's authentication. Then, they hash the message themselves. If their new hash matches the one they just decrypted, bam, that's integrity. It's brilliant.
Look, to pass the CEH, it's not enough to just memorize definitions. You've got to think like a hacker. You have to understand how these systems can be attacked, where their weak points are.
Here's a perfect example of a CEH-style question. It seems pretty logical, right? Encrypting something twice has to be better than once. So why is double DES totally insecure, but 3 DES was the standard for years? Well, it all comes down to a really clever attack.
And that attack is called meet in the middle. Instead of just trying to brute force two keys one after the other, an attacker works from both ends. They take the original message and encrypt it with every possible first key. At the same time, they take the final encrypted message and decrypt it with every possible second key. They just keep going until they find a match in the middle. It's a clever trick that makes breaking double DES way faster than you'd think.
And here's the kicker. This is why 3DS isn't just DES times 3. That specific encrypt-decrypt-encrypt sequence was designed for one reason: to stop the meet-in-the-middle attack cold. It's a direct countermeasure, which is what made it so much stronger than just doing DES twice.
So, as a security professional, this is your mantra. Just repeat after me. I will not invent my own crypto. I will not use old, broken algorithms like MD5 or DES. I will always use modern, publicly reviewed, standardized algorithms like AES and RSA.
And this chart just says it all, doesn't it? It shows the relentless march of progress. 56-bit DES was once top of the line. Now, you can crack it in a few hours. Even 3DES is considered vulnerable. This is why we're always pushing for stronger standards like AES to stay one step ahead of the computers that are trying to break this stuff.
And we'll leave you with this final thought to chew on. The security of algorithms like RSA is based on one simple fact. It's really hard for normal computers to factor huge numbers. But for a quantum computer, that problem is trivial. So the entire field is now in a race to develop post-quantum crypto to prepare for that future. As a security pro, the learning, believe me, it never ever stops.